Greetings. We will discuss the question, what is quantization today? Okay? What exactly do we mean by quantization? So, we have Galileo, Newton, Lagrange, Hamilton on one side and de Broglie, Schrodinger, Heisenberg, Born, Jordan on the other. And we know that the theory of classical mechanics is superseded by the theory of quantum mechanics. So, what exactly are we doing? So, at a fundamental level, we are asking the same question, which is at the bottom of this slide. How do you describe the state of a system and how does it evolve with time? Okay? And then when you get into quantum mechanics, we will have the uncertainty principle delta q delta p greater than or equal to h cross by 2 and so on, and we certainly are eager to know what is delta q and what is delta p, but even before we ask this, we must ask what is q and what is p, right. And you have this Young's double slit experiment, and I showed you a simulation which Uday did for Young's double slit experiment with waves. And here is a simulation that he did for waves for Young's double slit experiment with particles, okay, with electrons. And the experiment is the same. What you have is a source of electrons and then a double slit, okay. And you open one slit, close the other, you get the distribution that you would expect from your experience. You open either of the two slits, but keep the other closed, no problem there. But once you open both the slits, you get interference just as you did in waves, in the experiment with waves. Now, this is again really very shocking, because when you open the other slit, you expect more electrons to come through, and instead they seem to be disappearing from some region. So, all of a sudden there is some shocking situation which is happening, and you are not able to answer from which slit the electron came through. And our idea of a particle is that it would go from one or the other. If this room has got two doors, you are going from either one or the other. And you do not want to imagine a situation that you do not know from which door you came through. And just because the electron cannot argue with us, we have this situation in which we are not able to tell whether it came from slit 1 or slit 2. And if you cannot tell from which slit it has come, you are not able to tell its trajectory, you are not able to tell its path. And if you are not able to tell its path, you have no information about the position and momentum of the electron, because the classical definition of a path is the locus of the q comma p. Okay, q comma p is what describes the state of a system. A point represents the state of the system in the phase space. Q dot and P dot, the Hamilton's equations tell you how Q and P change with time. Okay? And if you trace Q and P at every instant of time, then you would have tracked the trajectory of that object in the phase space. So, the trajectory, the path requires simultaneous information of position and momentum. And if you are not able to say from which slit the electron has come, if you are not able to say from which path the electron has taken, then you abandon the notion of path, you reject that as not useful anymore, and along with that you have to get rid of this idea that the state of a system is described by position and momentum. These two measurements are not compatible with each other. Okay? So, what happens is that the description of the state of a system by a point in phase space has to be abandoned, and the relationship that we have in classical mechanics, that a state is given by q comma p, that must go. And if that goes, what enters is a description of the state of a system in terms of something else. It is a completely new system, and this completely new system is quantum mechanics. This is quantum theory. This is quantization. So, q comma p equal to state exits. The state of the system is represented by a vector in the Hilbert space. Okay. What about dynamical variables in classical mechanics? These are the ones in which we are interested anyway, and these must be represented by operators, because you have these vectors, these are operands, these are operated upon by the vectors, and the relationship with observables becomes transparent, becomes clear as you develop the algebra further, as Dirac tells us. Okay? So, this marks the exit of classical mechanics, and this is where quantum theory enters, and this is quantization. Okay? You are using a different formalism. The grammar of the description of the physical universe is different. It is no longer what the Hamilton's equations or the Lagrange's equations gave you. It's a different grammar altogether. It's a different algorithm. It is a different description. It is a different mathematical system. And the replacement of the older system by the new system is quantization. Okay? So, certainly we have all seen the relation delta q delta p greater than or equal to h cross by 2. But before we ask what is delta q and delta p, we must know what is q, and since we have agreed that dynamical variables must be represented by operators, our description, our whole vocabulary, our terminology of position must be replaced by the position operator. And in the position representation, what would be the q operator? It is position q times the unit operator. We also need momentum. So, what is momentum? It is going to have to be the momentum operator, right? And now, we know what the position operator is. We agreed in a very simple manner that q is equal to q into the unit operator, but we do not know what is p now, all right. So, we have to ask that, and we will find out what the momentum operator should be in the position basis, because we have our basis is the position basis, and that is what makes q as q times a q operator as q times the unit operator, but we have to find out what will be the momentum operator in the position basis. So, what we do know about the position space, which is homogeneous, okay? Momentum is the physical quantity which we know is conserved under translational invariance. Momentum is the generator for translation. And in our previous class, we discussed what is the translational operator, okay, the operator for infinitesimal translation. So, if you have an infinitesimal translation through ds, the operator for that, we agreed, will have to be 1 minus I ds k, where k must be Hermitian. This is the result that we got in our previous class, and this was arrived at by seeking some properties which the infinitesimal displacement operator must satisfy. We decided that it should be unitary. If there are two consecutive displacements, they should be represented by the sum of the two displacements. We also agreed that in the limit that the displacement itself goes to 0, it should be an inverse operator, right. You should get the unit operator if the magnitude of the displacement goes to 0, and the inverse of this must be given by tau of minus ds. So, that is what made it unitary. So, these are the properties that we desired, and we got this expression. So, we know that the infinitesimal displacement operator is given by 1 minus I ds k, and then k, since we know that it must have the dimensions of 1 over length, we decided that the operator k must be represented by the operator linear momentum by h cross, but we do not know what is p, what is the p operator. Okay? We still have not answered that. So, let us remind ourselves also of some definitions and interpretations that we introduced in our previous class. This is what we did toward the end of the previous class. So, you have an arbitrary state vector, we are working in position eigenbasis. So, here the integration over this projection operator gives you the unit operator. So, you project out the state alpha, which is an arbitrary state, on one of the position eigenkets, and essentially what you get is an expansion coefficient, and it is this expansion coefficient which is the wave function. Okay? So, this is the wave function. Then we recognize it to be the probability amplitude, we recognize its modulus squared to be the probability density, and when you multiply this density by an infinitesimal interval around it, you have the probability itself. So, these are some of the interpretations that we offered last time, and if you see the unit operator sitting between this expression for the norm of alpha, then this must be unity, and if you write this in terms of this wave function notation, so the left hand side is equal to the right hand side, and these two are obviously equal to each other, which is why there is an equality. But then this is just a matter of notation. This is the Dirac notation and this is the de Broglie Schrodinger notation. Okay? So, you can write this expression in the de Broglie Schrodinger notation, and what you find is that the integral psi star psi is equal to unity, which is a statement of what is called as normalization, because what you are doing is essentially you are simply adding up the probability, and the total probability of finding a particle somewhere in space when you integrate over the whole space must of course be equal to unity when probability is read on a scale from 0 to 1. Okay? So, these are the interpretations that we work with, and now we proceed to seek what is this momentum operator. So, let us take this infinitesimal displacement operator and operate by it on an arbitrary vector alpha. Okay. Alpha is completely arbitrary, it is some state vector. All we know about it is that it is a vector in the Hilbert space, it does not matter what it is, and we know that the infinitesimal displacement operator has this form. So, we go ahead and operate on this. Okay. We can insert a unit operator over here. We have resolved the unity in terms of these projection operators in the position eigenstates. Okay. I carry this relation to the top of the next slide, all right. And now, having done this, I ask what is this operator going to operate on? It operates on everything to its right, but this operates on a vector in the Hilbert space. The vector is here. This is the scalar, right? This is a function, this is a complex number, it is a function. The only thing which is going to be sensitive to this operation is the ket vector x prime. So, which is why this is put together over here. Okay. And what does the infinitesimal displacement operator do to this ket? It is an infinitesimal displacement operator. So, it will shift the label in the ket x prime by the infinitesimal displacement ds. So, that is what it has done. So, x prime goes to x prime plus ds. So, I have carried out this operation now. Having done this, I relabel x prime plus ds as x double prime, and I am going to integrate over all x prime labels, but effectively I can integrate over the x double prime label also, okay, because I have only shifted the label. It is a dummy label, it is going to be integrated out. It is like counting the number of persons in this room, and I begin here and say this is 1, 2, 3, 4 and so on, finish counting over here, okay. Or I count beginning here and this is 1, 2, 3, 4 and so on, and complete the counting, I get the same number, right. So, integration over x prime and x double prime is essentially the same, okay. So, this integration which is over x prime is now over x double prime. So, I am only playing with the right hand side, the left hand side is always the same, okay. But having replaced x prime by x double prime, I do not want to see x prime in the integrand. So, this x prime becomes x double prime minus ds. So, this is just a shift of indices which I have to do in a consistent manner, okay. So, let me write this result over here. So, having done this, I recognize that what I have over here is nothing but a wave function. It is the probability amplitude of the state vector alpha being at the point x double prime minus ds, okay, because this is the wave function, right. So, here the argument is not x, but x double prime minus ds. So, this is the probability amplitude sure enough, but not at the point x double prime, but at a shifted point which is close to it. It is pretty close, right, but it is not there, it is not at x double prime, it is at a neighboring point. So, now we know how to get it, because the directional derivative of any wave function is nothing but the component of a gradient along that direction, okay. This is the directional derivative, and therefore, the change in the function itself is the component of the gradient in that direction multiplied by the magnitude of how far it is from that point, okay. So, ds, the delta psi, the change in the function from one point to the next point, because these functions are continuous, okay, it is a continuous function, it will be the value of the function at a neighboring point. So, this function which is a function at a neighboring point x double prime minus ds, this we know from Taylor expansion of this function is nothing but the value of the function at x double prime minus ds dot del psi, okay. This is the gradient with respect to the double primed variable, okay. So, good enough. So, now all we have to do is to replace this function by these two terms, by the sum of these two terms. The sum of course appears as a difference because of this minus sign. So, that is what you will put, and you will have under the integration two integrals, one coming from the first term which is psi alpha x double prime, and the second coming from this term with a minus sign which comes here, okay. So, this is pretty good. So, now you have an operator. I extract the operator from this rectangular bracket which is 1 minus ds dot del double prime, because this is like the unit operator operating on psi x double prime, and this is like the ds dot del operator operating on this, okay. So, I write this in terms of the operators, okay. So, here it is, you can write it in terms of the wave function in the de Broglie Schrodinger notation or in the Dirac notation, and I will use them equivalently. You can go back and forth from one to the other without any hesitation, right. So, this is what we have got. Now, you have two terms. I write these as two different integrals, one coming from this integration over x double prime. You have got the unit operator sandwiched between this ket and this vector which is a complex function, right. And then the second term is again an integration over x double prime with this ket x double prime and then the second term ds dot gradient operating on this function, the minus sign is coming here. Okay. So, what do you get from the first term? The first term simply gives you alpha, because this is the unit operator. What is left is the projection operator. You take integration over the whole space, so you get the unit operator. It's a resolution of unity, right? So, you get only this alpha from the first term, and from the second term you have this term which is written exactly as it was in the previous step. So, now you have got a left hand side equal to the right hand side. So, you cancel common terms, okay? You cancel common signs, right, and that leaves you with this expression over here, that you have got this operator operating on alpha, which is given by this integral on the right hand side. Okay? So, now we are interested in getting the coordinate representation of the momentum operator. So, we project it, this whole equation we project on a position eigenket. Okay? But when you are taking the projection, you must use the okay. So, when you project it, you must take the projection on the adjoint of the vector x prime, adjoint of the vector x, right. So, you take this projection now, okay. You have this is the projection of the left hand side, and this is the projection of the right hand side. Now, this is integration over x double prime. This is the particular x. This x double prime is a dummy label, it gets integrated out. X is not a dummy label, it is one label which has been chosen, because we are asking what is the projection of this on one of the position eigenstates. So, this is not a dummy label, and this can therefore be brought under the integration without any hesitation. So, it comes here, okay, and now you get a complex function over here. This is actually not a function, but a functional. You will recognize it to be the Dirac delta function which we introduced in our previous class. So, this is the Dirac delta. Okay. So, you write the Dirac delta now, and what does the Dirac delta do to the integral? It will kill every value of the integrand except when x double prime is equal to x. Okay. So, let us see that happen in the next step. The right hand side will, after the integration is carried out, be reduced to only one value corresponding to x double prime equal to x. So, this x double prime equal to x has survived, and rest of the terms are here. The I and h cross were here, I have brought them to the right hand side. So, h cross goes to the numerator on the right hand side, and I comes to the denominator on the right hand side, but then it goes to the top and picks up a minus sign. All right. So, this is a scalar product along an arbitrary displacement, right. And since this is completely arbitrary, you must have the equality between this matrix element of momentum in this state with what is left over here, which is minus I h cross gradient, and then you have got this function which is in fact the wave function. So, do not forget that. So far so good. Okay. It is beginning to look a little familiar, okay, but it is not still the result that we think it is. Okay. So, now you consider a particular alpha. Alpha that we had chosen was an arbitrary vector, and since it was arbitrary, I can choose it to be anything, and I choose it to be a position eigenket belonging to a value x prime. So, with this choice, I have the matrix element of the momentum operator in position eigenkets, okay, to be given by this alpha now is x prime, which of course we know is the Dirac delta. So, this is also fine, all right. This is beginning to look even more like what we think it is, but it is still not what it is, all right. So, that will come very soon in the next step, I think. So, here we are. Now, if you consider the matrix element of momentum operator not in position eigenstates, but in two arbitrary states, whatever what, anything. So, I replace x prime by an arbitrary state alpha and x by another arbitrary state beta. I write the same on the right hand side, but I sandwich a unit operator on either side of the momentum operator, and then I resolve the unit operator in position eigenstates. So, this is the resolution of the unit operator in the position eigenstate for this one, and this is the resolution of unity for this operator. But because there are two integrations, I use a different dummy here. It is dummy, but it is different. Okay? So, this is integration over r and this is integration over r prime, and both get integrated out. And now, let us write the integration symbols away from this mess, so that we can begin to interpret these terms. Okay? So, this is the same relation, except that we have written it out in a slightly neater form. Okay? And now, we recognize that here you have got the matrix element of the momentum operator in position eigenstates, and this we obtained on the previous slide, that the matrix element of the momentum operator in the position eigenstates is nothing but minus I cross gradient and the Dirac delta. So, we can use this right hand side to come here. So, this right hand side comes here, and we carry out the Dirac delta integration over r prime, and we are left with only integration over r, and only those values in the integrand survive for which r prime is equal to r. So, here we are. Okay? And I can write this in the Dirac notation or in the de Broglie-Schrodinger notation. This is nothing but the wave function psi alpha. This is nothing but the complex conjugate of psi beta. Okay? So, let us look at this result over here, right. So, this is coming because the momentum is the generator of translations in homogeneous space, okay. And we find that the matrix element of momentum operator in two arbitrary states alpha and beta, no matter what alpha and beta are. Now, this is the important thing. We did not pick alpha and beta to be anything specific. In the previous steps, we were working with position eigenstates, but now we do not care what it is. Alpha and beta can be just about anything. So, these are arbitrary vectors in the Hilbert space, and no matter what P is, which also means that no matter what this wave function is psi alpha, and no matter what this function psi beta is, this relationship is valid. Okay? These are completely arbitrary, which means that the operator for momentum must be this, what is in the square bracket. So, we do not have to think of it as a postulate of quantum mechanics, as sometimes some people suggest that. It comes so neatly from the consistency that we have in the algebra of the Hilbert space. Okay? There is no choice. Okay? It has to be this. This is the correct form because it comes from the very simple consideration of what an infinitesimal displacement operator is, and the infinitesimal displacement is generated by the momentum operator, and That is the beauty which we are seeing over here in this relationship. So, we needed the operators for position, which we decided was position times the unit operator, and the operator for momentum is what we needed, and this must be minus IH cross the gradient operator. There is no mumbo jumbo about it. Okay. You do not have to worry, should it be plus IH cross or minus IH cross? No, it has to be minus IH cross. Everything has come out neatly. All right. So, this is now quantization. Exit QP as the representation of the mechanical state of the system. Enter state vectors and operators. The operator for position is Q operator, which is Q times the unit operator. Operator for momentum is the minus IH cross gradient operator. This is quantization. This is quantization. We have not defined quantization in terms of discrete energy states. Okay? Discrete energy states is quantization, but quantization is not discrete states. Okay? So let me explain this. You've got the hydrogen atom spectrum, which I think all of you know from your high school. All right. So, you have got n equal to 1 state, and then n equal to 2 state, and then 3 and 4, and you keep counting as long as you can, and your lifetime will not be enough to count all the states. There are infinite states, and then the Rydberg series, as it is called, it converges to the series limit, which is your 0 of the energy scale. Okay? These are of course discrete, and the reason they are discrete is because the Schrodinger equation, which we will be introducing very soon, is a differential equation whose meaning becomes relevant only after you impose some boundary conditions, right. Any solution to a differential equation has got no meaning unless you put the boundary conditions, because you will have these constants of integration coming when you solve the differential equation. So, you are looking at the bound state spectrum of the hydrogen atom, and when you are looking at the bound state spectrum of the hydrogen atom, it is discrete, and it is discrete because of quantum mechanics, and that is what I said, that discrete eigenspectrum is quantum mechanics, but quantum mechanics is not just discrete spectrum, because if you give some energy to an electron in the hydrogen atom, okay, you can give a 13.6 electron volts and knock it out. Okay. You can give 13.7, 13.8, 13.80653, 13.8065379, right. And you can keep increasing that energy continuously. And what is going to happen? The electron will get knocked out, and the energy difference it will carry as its kinetic energy. That is Einstein photoelectric equation, right. That excess energy it will carry as kinetic energy, and it will go into the continuum, right, which are positive energy states. It goes into an eigenstate of the very same Hamiltonian, of which the discrete part is also an eigenspectrum. Okay? And you have got a continuum of energy states. They are all eigenstates of the very same Hamiltonian. Only thing is that these continuum states are not square integrable. How to normalize them? So you have a discrete eigenspectrum here, okay, and a continuous eigenspectrum which represent eigenstates of the very same Hamiltonian. Both are quantum mechanics. It is the same Schrodinger equation whose solutions belong to the discrete state and the continuum states. So, quantum mechanics is not having discrete energies. Discrete energies is quantum mechanics, but quantum mechanics is more than that. Okay? It allows for continuum states also, and in fact, there is a big world of quantum physics, the quantum collision physics, which all deals with, which all work with these continuum eigenstates. In fact, there is a formulation in terms of the S matrix theory, which is all with reference to the continuum states of quantum mechanics. So, the only difference is that the boundary conditions are different. The boundary conditions on the same differential equation, the same Schrodinger equation for the discrete states are such that the wave function must go to 0 as r goes to infinity, okay? Because it is a bound state. So, the amplitude must go to 0 in the asymptotic region. As r goes to infinity, the amplitude must vanish. Whereas, for a continuum states, if you give the electron an energy which is more than the binding energy, more than 13.6 electron volts for the hydrogen atom, right. If you give it like 14 electron volts or 14.6035879 electron volts, you can change that number continuously, right. Then the electron gets knocked out, it is no longer bound to the parent hydrogen atom, it goes away. Where does it go? It keeps going away and away and away and away, farther and farther and farther. It goes to infinity, and the only thing which is beyond infinity is also infinity. So, it just keeps going, right, and which means that the radial function as r tends to infinity is not equal to 0, and this is what comes in the way of defining the square integral. So, these have to be normalized in a different way, but I will get to that at some other point. They are normalized using what is called as what is again the Dirac delta comes in handy over there, but that is for a later discussion. And essentially you get oscillatory functions which do not go to 0 as r tends to infinity for the continuum states, whereas for the bound states they go to 0 as r goes to infinity. Okay. So, we have, this is the discrete part of the hydrogen atom spectrum that you have studied in your high school, and you have n, l, m to be the good quantum numbers, and the energy is given by 1 over n square and so on. So, all that is good, but there is a difference that the continuum eigenstates are also eigenstates of the very same quantum Schrodinger equation. So, quantization is not equal to discrete energy spectrum. Discrete energy spectrum is quantization when you apply it to bound states, okay? But states are not always obliged to be bound. Sometimes they are, sometimes they are not, okay? So, now we understand what is quantization, which is to address the central problem in mechanics. It aims at addressing the same question: how do you characterize the state of a mechanical system, and how does this state evolve with time? Okay. We know that it cannot be described by position and momentum as dynamical variables. Its temporal evolution cannot be described by the rate at which q changes with time, which is dq by dt or by dp by dt, okay, which are given by the Hamilton's equations, and whether you write it in terms of Hamilton's equations or Lagrange's or Newton's, they are all equivalent to each other, but the language is different. Okay. One is based on causality and determinism, which is a Newtonian formulation, and the Lagrange's and the Hamilton's formulation is based on the principle of variation, the Hamilton's principle of variation, the principle of least action. So, that is the basis for the Hamilton's equations, and this question sticks with us. but the answer cannot be based on Newton, Lagrange and Hamilton's equations. So, the answer will have to be in a different framework, which has to be in terms of what we call as quantum theory, and this answer involves the description of the state of the system by a vector in the Hilbert space, and how it evolves with time is given by the rate at which this vector changes with time. So, the partial derivative of this vector with time is what we are looking for. So, we know that the state of the system is described by a vector in the Hilbert space, and how will it change with time? We have to find what is this right hand side. IH cross, you can think of it as just a constant over here, but your fundamental question is how does it change with time? Okay? If we answer this question, we would have answered our primary central question in mechanics. How do you describe the state of a system and how does it change with time? So, when we get the right hand side of this equation, we will find that the right hand side of the equation is nothing but what will give you a left hand side equal to the right hand side, which will be nothing but the Schrodinger equation itself. Okay. So, that is something that we will be looking for. Okay. The Schrodinger equation gives you the rate at which the wave function changes with time. It is the time derivative of the wave function, del psi by del t, and some of you have seen this earlier. It is IH cross del psi by del t equal to H psi. Okay. So, that is the Schrodinger equation, but why should it be H psi is something which we will discover in the next class, next or one of the next classes. It is not possible. You can perform the experiments with bullets, okay? And suppose you fire a bullet at the speed of 100 kilometers an hour or 100 kilometers a second, let us say, okay? 100 kilometers a second, and you fire the next bullet only tomorrow. So, you know that the bullet has to have reached the screen before you fire the next bullet. Okay? Where is it going to be? It has to go through the slits, but then when you see the result, okay, after 10 years, after a number of bullets have been fired, okay. So, after 3,650 bullets are fired in 10 years, okay. Every day you know that I fired only one bullet, and it had to go through one or the other slit according to my classical understanding of trajectory. But then if you see the intensity pattern at the end of 10 years, if both the slits are open, you will see the interference. How does it come? That is how nature is. So, this is what we stated earlier also in one of the previous classes, that probability and statistics is intrinsic to the laws of nature. This is how nature is. This description of nature is correct because it describes nature correctly. If you do this experiment, this is exactly what you will find. In fact, when Feynman discussed this experiment with waves and double slit experiment with waves and with bullets, which you find in his book and lectures, this experiment was not done at that time. This was in the early 1960s. Subsequently, the experiment has actually been done and the results are exactly what Feynman described much before the experiment was ever done. That is quantum mechanics. So, the predictions of quantum mechanics turn out to be true. The reason we say that okay, it is the correct description of nature, because you do not find any exception to it. Okay. It does provide the correct description of nature, whereas classical mechanics describes nature in terms of that q dot equal to del h by del p and p dot equal to minus del h by del q. That does not give you the correct description of nature. It gives you a reasonably good description in many situations. And the reason it gives a reasonably good description when you are describing the trajectories of tennis balls and motor cars, okay, and when you kick a soccer ball, all right, you get a fairly good description by solving Lagrange's equations or Newton's equation. It is because classical mechanics is a good approximation in those situations, not because it is correct. It is a fairly good approximation in those situations, not because it is a correct theory. It is not correct theory. If it were correct, it should be able to always be correct. So, it is not correct. It seems to be correct in some situations, because those approximations are sufficient for those situations. But when you apply it to some other situations, that is not correct. Whereas, if you apply quantum mechanics to anything, including the soccer balls, it is correct. So, get it out of your mind that quantum mechanics is used only for small particles. It is not that you have got one theory for small particles and one theory for big particles. You have got only one correct theory, which is quantum mechanics. It works for small particles, electrons, positrons, protons, atoms. It also works for soccer balls, Earth. You can solve the Schrodinger equation for a galaxy, and when you do that, you say the mass of the sun is ignorable. You can do that. Okay? So, quantum mechanics is always correct. Classical mechanics is sometimes not fully correct, but fairly good approximation. So, when you do not need anything better than that approximation, you can go ahead and use classical mechanics. It is not, and the reason it gives a fairly good answer in many situations is because the theory is not absurd. Okay. So, when you replace classical mechanics by quantum mechanics, it is not because the earlier theory was absurd. Okay. When you replace what Aristotle thought about why objects fall, this is an example which I give in my classical mechanics course, that if you let go of a bottle of anything and let go and it falls, Aristotle said that okay, the reason it is coming is because the earth is the natural abode of this, and objects fall just as horses return to their stables. You replace that by Newton's theory, by gravity. When you do this, it is because Aristotle's model was absurd. Newton's model is also, it has to be replaced, not because it is absurd, but because it is not good enough. It is good, but not good enough. It has to be improved upon. It does not account for so many things in nature, and because it does not account for everything in nature, it is not a universal law. So, you look for a universal law, and here it is. It is the Heisenberg principle of uncertainty, it is the Schrodinger equation, it works. You cannot find a situation where it does not work. At least that has not happened until now. If by any chance it happens tomorrow, you will need to improvise this. It seems very unlikely, but this is not impossible. It is what I might call as highly improbable.